What if I told you that the future of forced induction isn't just about cramming more air into your engine? It's about doing it smarter, faster, and with electricity. Turbochargers and superchargers have been around for decades, forcing more air into engines to make more power. Recently, conventional turbos and superchargers have been joined by electric versions of both, changing how modern performance engines deliver boost, reduce lag, and improve response. But despite the similar names, these two technologies work very differently. So, what are these electric versions? How do they work? And are they actually better? Let's find out in this video. Turbochargers and superchargers are both forced induction systems. Their job is simple: force more air into the engine. More air means more oxygen, and more oxygen means more fuel can be burned. More fuel and oxygen mean more power. That's why a smaller turbocharged engine can make more power than a larger engine. It's getting more out of every power stroke. The main difference is their power source. Turbochargers use exhaust gases to spin a turbine, which drives a compressor on the same shaft. Superchargers use a belt connected to the engine's crankshaft to drive the compressor directly. Engines with a supercharger or turbo can produce much more torque compared to a naturally aspirated engine. The downside of a turbocharger is that it takes a moment for the engine to produce enough exhaust gases to spin the turbo up to a workable level. A supercharger doesn't have such a lag, but spinning the supercharger does put drag on the rest of the engine and takes a pretty significant toll on engine efficiency. So if you assume that adding the electric part to both of these systems is to help get rid of these downsides, then you'd be right. To understand how an electric turbocharger works, we first need to look at a conventional turbocharger. A turbocharger has two sides: a turbine on the hot side, driven by exhaust gases, and a compressor on the cold side, which forces more air into the engine. The two are connected by a shaft, so when exhaust gases spin the turbine, the compressor spins with it. A wastegate is used on the exhaust side of the turbo to regulate the gases. A blow-off valve is used to expel excess air after you take your foot off the gas pedal. It's an incredibly efficient system because it recovers energy that would otherwise be wasted through the exhaust. But there's a limitation. When you shift gears, or the engine RPM drops, exhaust flow decreases, causing the turbocharger to slow down. Then, when you accelerate again, the system needs time to rebuild exhaust pressure and bring the turbo back up to speed. During that time, the engine is still waiting for boost to build. That delay between pressing the accelerator and receiving full boost is known as turbo lag. So how do we solve this problem? What if we could spin up the turbo before the exhaust gases arrive? What if we didn't have to wait? That's exactly what electric turbochargers are designed to do. Electric turbochargers are an advanced form of forced induction that combine an electric motor with traditional turbocharging principles. This electric motor is mounted directly onto the shaft connecting the turbine and compressor. When you hit the throttle, instantly that electric motor spins up the compressor. We're talking 70,000 to 150,000 RPM in a fraction of a second. Boost is already building before any exhaust gas reaches the turbine. As exhaust flow increases, it starts spinning the turbine side. Now you've got both the motor and exhaust working together. This means you can spin up the turbocharger independent of exhaust gas flow, which has all sorts of benefits. Instead of waiting for exhaust gases to build boost, the electric motor can spin the compressor almost instantly, dramatically reducing turbo lag and improving throttle response. It also allows the turbocharger to maintain boost more effectively during gear changes and low RPM conditions. Another major advantage is control. Because the system can precisely monitor and manage turbocharger shaft speed, automakers can safely operate the turbo closer to its performance limits while improving efficiency and responsiveness. Garrett states up to a 10% efficiency improvement for their e-turbo plus mild hybrid combo. However, electric turbocharger disadvantages include higher power consumption and more complex system requirements compared to conventional turbos, resulting in increased costs. These require a powerful electrical system, because spinning a turbocharger electrically at extremely high speeds demands a significant amount of power. Engineers have been trying to build electric turbochargers since the 1990s. Companies such as Borg-Warner proved the concept could work, but the technology of the time simply wasn't ready. 12-volt electrical systems couldn't deliver enough power to spin a turbocharger electrically, so the idea was shelved. Everything changed in 2014 when Formula One introduced the MGU-H. By mounting an electric motor directly onto the turbocharger shaft, engineers could almost eliminate turbo lag while also recovering energy from the exhaust. Mercedes-AMG became the first manufacturer to bring this technology to a production car, with the 2022 AMG C43. Its 2-liter 4-cylinder engine uses a Garrett-built E-turbo, powered by a 48-volt mild hybrid system, with the electric motor on the turbo shaft spinning up to 175,000 RPM. On its own, that engine makes 402 horsepower. With the 48-volt motor's assist, total output climbs to 415 horsepower. AMG then took the idea much further with the C63S E-Performance. It uses the same basic E-turbo concept, but built around a full 400-volt hybrid system, instead of just 48 volts. On its own, the turbocharged 2-liter 4-cylinder makes 469 horsepower, more than some V8 manage, and combined with the rear electric motor, the whole car produces 671 horsepower and 752 pound-feet of torque. The 2025 Porsche 911 Carrera GTS pushes the idea even further. Its newly developed 3.6-liter flat-six engine is equipped with a single, massive E-turbo. The system is so advanced that Porsche completely eliminated the traditional mechanical wastegate. Instead, the boost is regulated entirely by the electric motor generating electromagnetic drag. It harvests up to 11 kilowatts of electrical power from the exhaust stream, which is used to feed another electric traction motor inside the transmission. Unlike a turbocharger, a supercharger doesn't have to wait around for exhaust gases. It is connected directly to the engine. The moment the engine speeds up, the supercharger speeds up too. That means the boost is available almost instantly. No waiting for a turbine to spool up. No noticeable lag. Just immediate response when you press the throttle. And that's exactly why superchargers are still popular in many performance cars. But there's a catch. Because a traditional supercharger is driven directly by the engine, it takes power to make power. The engine has to use some of its own output just to keep the supercharger spinning. That's known as parasitic loss, and it's the biggest downside of a supercharger. While you get instant boost and great throttle response, you also sacrifice some efficiency and burn more fuel in the process. That's where the electric supercharger comes in. An electric supercharger is still a supercharger. It's still compressing incoming air and forcing it into the engine. The difference is that instead of being driven by a belt connected to the crankshaft, it's driven by an electric motor. That means it can generate a boost without stealing power directly from the engine. Here's how it works. The moment you press the accelerator, an electric motor spins up the compressor. That compressor starts forcing more air into the engine. Because the compressor is powered electrically, boost can be generated almost instantly, regardless of engine speed. Electric superchargers are particularly effective at low engine speeds, where conventional turbochargers typically struggle to generate boost. Imagine pulling away from a stoplight or accelerating out of a slow corner. The electric supercharger delivers strong, low-speed torque immediately, making the engine feel larger and far more responsive. Of course, generating a boost electrically isn't free. Spinning a compressor requires a lot of power, which is why most electric superchargers rely on an electrical system. As a result, they are most commonly found in mild, hybrid, and advanced performance vehicles. One well-known example is the system used in the diesel engines of the Audi SQ7, where an electric supercharger helps deliver boost before the turbochargers have a chance to fully spool up. Another limitation is operating duration. Unlike a conventional supercharger that can run continuously as long as the engine is running, electric superchargers are usually designed to provide short bursts of boost. Running the electric motor continuously would place a heavy load on the vehicle's electrical system and quickly drain available energy. For that reason, manufacturers often use electric superchargers alongside conventional turbochargers rather than as a complete replacement. In fact, some modern engines combine an electric supercharger with a conventional turbocharger. At low RPM, the electric supercharger provides an immediate boost. As engine speed increases and exhaust flow builds, the turbocharger takes over and provides sustained boost at higher loads. This combination delivers excellent low-speed response, strong high-speed performance, and improved efficiency all at the same time. Of course, none of this comes for free. Adding an electric supercharger means extra hardware, a powerful 48-volt electrical system, and higher manufacturing costs. So, although both use electricity, they solve different problems. An electric turbocharger helps a turbocharger react faster, while an electric supercharger creates boost directly, without waiting for exhaust gases or relying on a belt-driven compressor. As vehicle electrification continues to evolve, these technologies are changing the way performance engines deliver power and giving us a glimpse into the future of the internal combustion engine. Now you know how electric turbochargers and electric superchargers work. But these are just the latest evolution of forced induction. If you want to dive even deeper, I've got 2 videos waiting for you. If you're curious about the different types of turbochargers, from twin-scroll and variable geometry turbos to sequential and twin turbos, click the video on the left. Or if you want to explore the different types of superchargers, including roots, twin-screw, and centrifugal designs, click the video on the right. Thanks for watching, and I'll see you in the next video.